When pulling into a station, attention naturally goes to the metal boxes on the concrete islands. We assume those visible dispensers are actively pulling gasoline from the earth. They do none of the heavy lifting. The roadside pump is essentially an empty kiosk, housing a digital screen, a flow meter, and a handful of valves. The true machine operates directly beneath the concrete. It's a tightly controlled, highly pressurized subterranean vault, holding tens of thousands of gallons of explosive fluid. Buying fuel is an entirely mundane chore, entirely dependent on a massive, hidden infrastructure, operating just inches beneath your shoes. A busy station requires a massive inventory of liquid on hand to survive the daily rush. Storing tens of thousands of gallons above ground would demand the square footage of a chemical plant, leaving the tanks entirely exposed to traffic and extreme weather shifts. In the mid-20th century, operators solved this geometry problem by burying basic bare steel underground storage tanks. The damp earth quickly caused the buried steel to rust. Microscopic pinholes formed entirely out of sight, leaking raw gasoline into the dirt. A single gallon of that fuel can contaminate 1 million gallons of groundwater. Hiding the tanks underground cleared the surface for traffic, but it triggered a sprawling, invisible environmental crisis below it. Modern engineers replaced the steel with gigantic ribbed tanks constructed from advanced fiberglass reinforced plastic. These structures are entirely immune to rust and soil corrosion. This diagram shows the system's core defense. The tank is double-walled. The gap between the inner chamber and the outer shell, the interstitial space, is completely filled with a liquid brine solution and laced with digital sensors. If the inner wall cracks, fuel leaks into the brine. If the outer wall cracks, groundwater pushes its way in. In either event, the liquid level changes. The sensors immediately detect the pressure shift and automatically lock down the central pumping system. This closed-loop fluid trap freezes the entire station operation before a single drop of gasoline can reach the surrounding soil. Storing the fuel safely is only the first physical problem. The system still has to lift that heavy liquid up to the vehicle without relying on a surface-level suction pump. This vertical pipe diagram illustrates why suction fails. Pulling a heavy liquid upwards over a long distance creates a massive low-pressure vacuum inside the pipe. That vacuum boils the liquid fuel into expanding gas bubbles, choking the line in a phenomenon called vapor lock. To bypass vapor lock, engineers placed a submersible turbine pump deep inside the buried tank. Bathed directly in the fuel, it forcefully pushes a solid column of liquid upward from the bottom. Reversing the physics ensures a smooth smouth. However, it creates highly pressurized lines of explosive liquid running directly beneath the concrete, surrounded by moving, multi-ton vehicles. If a distracted driver jumps the curb and entirely demolishes the metal dispenser, ripping the equipment off its foundation, the pressurized underground line should theoretically erupt into a continuous geyser of gasoline. The only thing preventing that is an intentional weak point. A heavy metal fitting called a shear valve is bolted directly to the underground line, resting perfectly level with the concrete. Machined all the way around its circumference is a deep groove. When struck by a vehicle, the sheer physical force snaps the valve cleanly at that groove. The instant the top half breaks away, a spring-loaded metal flap slams shut on the bottom half of the pipe. The pump above ground is destroyed, but the highly pressurized underground line is permanently sealed tight. At the very end of the line, the nozzle handles the final human interaction. We trust it to stop the flow of gasoline the exact moment a car is full, despite the handle possessing no digital sensors, software, or electrical wiring. The mechanism relies on a principle called the Venturi effect. The sheer speed of the gasoline flowing out creates a suction force inside the handle. This pulls air through a tiny pinhole at the tip of the spout, holding the main fuel valve open. When the rising liquid inside the car's tank covers that pinhole, the nozzle suddenly pulls heavy liquid gasoline instead of light air. That sudden spike in vacuum pressure pulls a mechanical diaphragm inward, violently tripping a metal spring to shut the valve. The physics of the moving fluid itself acts as a perfectly autonomous emergency brake. Maintaining the vault's inventory requires moving massive amounts of liquid whenever an 18-wheeler delivery truck arrives. The truck uses absolutely no pumps. The driver connects the hose, opens a valve, and the sheer physical weight of 10,000 gallons of fuel drops into the earth at incredible speed. This cyclical flowchart maps the vapor recovery network. 10,000 gallons of liquid rushing down into the tank physically pushes 10,000 gallons of explosive, toxic fumes up a second hose, directing them straight into the truck's emptying metal belly. The truck arrives full of liquid and leaves full of vapor. This closed-loop exchange contains the explosive fumes, allowing the station to maintain a perfect environmental equilibrium during a massive volumetric transfer. Overseeing all of this, buried plumbing and physics, is a small digital console sitting quietly inside the convenience store, the automatic tank gauge. Deep probes drop straight down to the bottom of the buried vaults. Using magnetic floats, they monitor the exact liquid volume, the temperature, and the specific level of water condensation down to the exact millimeter. If the central computer detects a microscopic mismatch between the exact volume of fuel dispensed at the surface and the volume missing below ground, it executes an immediate station-wide shutdown. When the underground inventory drops below a strict threshold, this system automatically pings the regional terminal to dispatch a refill truck. The station orders its own inventory without any human intervention. Stepping back, the flat expanse of concrete covering the station acts as the protective roof for a highly regulated, self-sustaining organism. The surface interface of retail gasoline has looked largely the same for decades, but the subterranean machine beneath it has evolved into a fortress of advanced materials, precise fluid dynamics, and cascading mechanical failsafes. Swiping a card and lifting a nozzle is a seamless interaction with a tightly controlled explosive vault, operating so flawlessly beneath the pavement that you never have to think about it.